volumetric spanners in all norms.
Thank you, Andrew. Hi, everyone. So yeah, I'm going to talk about tight bounds for volumetric spanners in all norms, and you will shortly see what this means. And this is a joint work with Aditya Bhaskara and Sepide Mahabati. Okay. So this is basically the problem we are considering. So we are given a set of vectors, let's say V1 to Vn, in a d-dimensional Euclidean space. And the goal is to find some basis for this set of points, such that I can write every point in the input as a linear combination of the vector and the basis in a way that the coefficients in this linear combination are small. So meaning that here, the absolute value, if I write V as the sum of alpha I Vi for the Vi's in the basis, the absolute value of alpha i's are small. And I would like to have the bases as small as possible. So the size, we need to make it as small as possible. So this is basically the general idea. And actually, nothing prevents us of looking only at the absolute value or L infinity norms of the coefficient vector. And we can think of any norm of the coefficient vectors. So that's the goal. So I would like to come with a base with a small coefficient norm for all points in the input. And the size of base I need it to be as small as possible. So is the problem clear? Okay. And it actually seems, I mean, it seems to be a very important problem in the sense that people have rediscovered it several times. And it has been used in various applications. So, I mean, back in 1929, that was a basis defined by Auerbach. And basically what it was in terms of, in context of functional analysis, and it's a different language or more somewhat maybe a stronger result in general. But what it implies here is that for any compact set in a d-dimensional space, there is a basis of size d such that the L infinity norms of the coefficient is less than 1. Okay. And actually, it was, I mean, since it was a very useful concept, it was somewhat rediscovered in this learning theory community. And they use it for linear optimization problem and multi-arm bandit problems. And they call it actually barycentric spanners. Okay. So this is basically can be think of volumetric spanner with L infinity norm. This is basically what they're doing. And they show that there exists order size D. And basically, for instance, the application in online linear optimization multi-arm bandit was basically finding a basis for the exploration of space and and just try to optimizing the result using that basis. Okay. And later it was also, I mean, this term was proposed by Hasan Karnin Mecca and Hasan Karnin, where they also studied this object or concept for multi-arm bandit and now even experimental design and some more matrix-related problem. And now they consider it with respect to the L2 norm. So they would like to minimize to make sure that the L2 norms of the coefficient vector for all points in the input is small. And so, I mean, just to define it more formally again, so we are given a set of points, V1 to Vn, and we would like to find a subset of them specified by S, I mean, it's the indices, such that, I mean, all points can be written as a linear combination of just the points in the spanner, and the L2 norm is less than 1. Okay. Good. And the thing that they showed is that there exists for any set of points of, I mean, let's say for any n vectors, you can find at most 12 times d bases in time polynomial in n and d. Okay, and actually they show some existential result for any convex body. So it's here. I mean, it's they can efficiently compute it, but even for more, general case, they can show that there exists such a basis. Okay, and actually they raise as an open question whether. So they show that there exists a volumetric spanner of size 12 times d, and it's there is some lower bound that's showing that you need at least d plus 1. So, and it was a question that what's the right answer, and or I mean, if we can just shrink the gap. Okay, and it doesn't stop here. So again, it was also studied in this concept, I mean, this notion like what they called well-conditioned basis spanning subset. And it was basically used for, because of, its application in matrix sketching, low-rank approximation, and this problem by Dasgupta et al. And actually very recently in this talk this year, David Woodruff and Taisuke Yasuda, they used volumetric spanner result, what they call spanning subset, to improve a host of problem in matrix sketching. I mean, several problems related to low-rank approximation, column subset selection, and so on. Okay, and let me just again, define what they're using. So they're saying we have a set of vector we want to be n. We would like a volume, what they call, spanning subset. They call it the C spanning subset, which is a subset of vectors in the input, so that I can write any point in the input as a linear combination of the points in the spanning subset, and the L2 norms is at most C. So you can think of C anything. For their application, it was like 1 plus epsilon or something. And the way, they actually somewhat just use it as a black box in a sense, and they got it from the coreset result for John ellipsoid from this result by Todd. And in some sense, it's it was some. The Hazan et al. Got a better result. In the sense of the size was order d, but in their construction, they could get a spanning subset of size d log d, but in a better runtime. Okay. But there are, many applications that the size is important, so maybe it's then better to replace with this order d size. Okay, and actually, the main contribution in their work, they show that there are many applications for this volumetric span.
Do you mean poly-D and epsilon fine NNZ, or NNZ is in polynomial?
No, yeah, it's just actually plus NNZ, so yeah. What do you mean? So by you mean the exact relation, or?
Yeah, so number of non-zero entries, do you take that to some power also?
No. Okay. I just was to be fair with all algorithm. Yeah, but it's just plus NNZ. Yeah.
Thanks.
Yeah, thanks. Okay, good question.
Do we need to assume like all of our vectors have the same norm or something, or it doesn't
Not really.
matter?
If you have a large vector, that could actually help you in the.
So if I have a
linear
long vector, I would pick that, and it would make the coefficient of everybody
Yeah, that
else.
can actually help in some sense, right? But yeah, but it also works if all are scaled. That's say a bounded norm 1 or something. Okay, yeah, and I mentioned there are tons of applications. I just mentioned a few of them here, and they can use this spanning subset or volumetric spanner and get improved bounds for them. And actually, they showed in online version of this problem. Okay, but I'm not going to talk about the application. I'm focusing on the volumetric spanner itself here. And in particular, I'm going to show that the local search, a simple local search algorithm, get tight bounds for volumetric spanner. So we show that if you just run local search algorithm with the correct somewhat update rule, then you get a spanner of volumetric spanner of size at most 3 times d in polynomial time. And the local structure is very simple. It's just a single swap. Okay. And actually, I mean, we are addressing in some sense, right, this question by Hazan and Karnin. So we are shrinking the gap. And in compared to the prior works, so compared to the Hazan et al., I mean, there we are faster. And so actually, we didn't try to really optimize the runtime, but I mean, even just a simple implementation is just d squared faster. But I mean, the main thing is that our algorithm is much simpler compared to this. So I mean, to get a sense, I mean, they use a spectral sparsification by Batson, Spielman, Shrivastava, and it's a very heavy machinery, and they need to keep track of barrier potential function and then do some rounding afterwards. So it's quite heavy machinery they're using for that. And actually, I mean, they themselves also had some simpler construction for volumetric spanner, which use the order d times log d log n. I mean, the simplicity was actually important even for them. So this is important to come up because as it's have many application, and I mean, they want it to be just simple enough to be used in application. They actually desire for something simple as well. Okay, and just compared to the just recent line of work by Woodruff, Yasuda, and Todd, I mean, they're losing a factor of log d. Okay, so that's, I mean, clearly, I mean, the size in this construction is better. And another thing is that we can show that this local search is actually almost optimal for all norms. It's not for L2 norm or L infinity. And it's somewhat, I mean, just a single thing that works for everything. And in particular, just to, but I mean, it works for all norms, but the complexities are somewhat very different in different, yeah.
Just quickly, so the lower bound shown was basically the D simplex or the D plus 1 simplex?
Yeah, I think so, yeah. Yeah, we don't, yeah, it's not any fancy lower bound, so that's the, okay, good. So yeah, so when we have when p is equal to 1, we can show actually, there's somewhat simple argument, we'll go to it further in the talk, that even if you just not pick one of the points in the input, then the L1 norm of coefficient can get as large as square root n. And n here itself is exponential in d. Okay, so you cannot get really the L1 norm down to 1. So you have to pay almost a square root of the number of the things. Okay. And actually, we can get a matching bound here as well by just using the local search. And for 1 and 2, we can also now use the result from p equal to 1 and p equal to 2 to get these upper bound and lower bound results, sorry, lower bound and upper bound results. And I mean, we're just using Holder inequality and so on. And for p greater than 2, it's also easy that just the L2 spanner implies something for LP spanner, right? So when the L2 norm is less than 1, for sure, I mean, LP norm is less than 1, so the size is still, by the size of the spanner for L2 volumetric spanner, we get the same bound for LP volumetric. Okay. And actually, I mean, among one of the application that we wanted to highlight is minimum volume enclosing ellipsoid, or John ellipsoid. And this is basically saying, so you are given a symmetric convex body K, and the MVEE, or minimum volume enclosing ellipsoid, is the ellipsoid that the minimum volume ellipsoid that contains K. Okay. And we show that actually this local set also gives some coreset for this problem. So we can pick a set of points of size order d over epsilon, such that the volume of the input is less than 1 plus epsilon to the power raised to the power d times the volume of the MVE of S. Okay. And just to give a little bit about this as well, I mean, this is this is somewhat related to these contact points of convex bodies. And I mean, that's a stronger notion, actually. I mean, that's what we are showing here than what we are showing here. For instance, there is this result by Rudolfsson, and which was improved by Srivastawa, that showed that for any convex body K, you can find another one edge, such that its contact point with the John ellipsoid is small, and basically it's order of d over epsilon square. And this basically also imply a corset for MVEE in some sense. And so we knew that, but it's just order of d over epsilon square. And also, I mean, the prior works that actually got this well-conditioned base or a spanning subset, they rely on minimum volume enclosing ellipsoids. And their result, for instance, from the Todd, its result, the size was something like d log d plus d over epsilon. And in the prior work, it was like order of d squared over epsilon. Actually, I mean, the prior work in this line of research, they use MVEE to design volumetric spanner, but somewhat here, I mean, we are doing a reverse thing. So we are showing that the local search is giving a good volumetric spanner, and it also implies a good MVEE.
Do you improve the contact point result?
No. I mean, it's stronger, right? So it's basically saying that if you look at the MVEE and just scale it by 1 plus epsilon, it will contain K. But our result only can compare the volume. It doesn't say that strong condition. No, that doesn't. Yeah, so exactly. I mean, this is a weaker notion compared to that contact points thing. But it's similar exactly to the corset definition defined by Todd and this prior work. And actually, that's for them, it was enough for them to get this volumetric spanner guarantee. Okay. And actually, I mean, just conceptually interesting, if you think about some much simpler object, like if you're given a set of point and want to find the axis parallel bounding box of this point, you need also 2D many points. You just need to pick the extreme points along each axis, and that's basically a corset for axis parallel bounding box. So in some sense, I mean, we are looking at the ellipsoid, but the corset size is still the same as, I mean, this very simple object. And one thing is that in our approach, and actually maybe even I think also the earlier approach, you cannot hope for some strong type corset, and it's actually maybe interesting. I mean, which is also related again to contact point. So again, could be the case that we can preserve MVEE, but if we look at some ellipsoid for the corset like this, I mean, these black points are the points in my corset. But if I look at one ellipsoid that contains them, even if I scale them by some large constant factor, I may not be able to cover everything. Okay, so it's a bit different. Okay, and again, I mean, just to complete the contribution, we can use our volumetric spanner as a black box and just improve the bounds here using the results of David and TTIC. Okay, now let's go to local search. Any questions so far? Okay, so I promised you that the algorithm is very simple, and that's basically the algorithm. So this is the input. We are given a set of points n, and we just need some accuracy parameter delta and the size parameter r, which is larger than d, and r is going to be the number of vectors that I put in my volumetric spanner. And then I just output the volumetric spanner of size r. Okay, so it has just these steps. I initialize it with a set of vectors, and the initialization has two parts. So the first part is that I just pick d vectors in S by the greedy algorithm for volume maximization. and add them to my spanner. And then for the rest, which is r minus d, I just arbitrarily pick some vectors from the input. Okay. And then I work with this matrix, which is just outer product of the vectors in the spanner, and go through a local search algorithm. And in each step, I check whether there exists a vector in my set, in my spanner, that I can swap it with someone else out of it, such that the determinant of M minus VI transpose plus VJ transpose get larger by a factor of 1 plus delta compared to determinant of M. That's the thing. And if it was the case, I just make the swap and continue. OK, so just first of all, without loss of generality, we can assume that the vectors are of rank D. Otherwise, we can just focus on the span of the input. So for now, we know that they're of rank D. And one more thing. So if you're familiar with this local search algorithm of Madan et al., so they're using similar local search, but for different contexts of determinant maximization. It's very natural. We're also only just dealing with determinant here. OK, so now I'm going to show you, first of all, why it's run in polynomial time, why it terminates. Next, I will show you the guarantee or the approximation guarantee for volumetric spanner, why the coefficients are always less than 1 when I'm using this set of vectors. OK, so for runtime analysis, so the thing that I'm going to do is I'm going to keep track of the determinant of M. I show that initially it has a good value. At each step, I'm just increasing by some factor, constant factor. And the optimal thing cannot be too large. That's the plan. So in each iteration, I make sure that it's increased by a factor of 1 plus delta. That's simple. So I need to bound the initial determinant. So why initially I get something reasonable, at least for my purpose. And that's actually comes from the guarantee of the greedy algorithm. So let's try to bound the determinant of M, or M in it, the initial M. For that, let's T star be a subset of size D in the vector in the input that its outer product has the maximum determinant. Okay. And let's G be the set that it's returned by the greedy algorithm of the Sivril Magnus file. OK. So it's very simple. We can write the determinant of the initial matrix M by Cauchy-Wiener formula as just determinant as the sum of subdeterminants of size D. And in particular, we have just one of them corresponding to the greedy. And this is already larger than 1 over d factorial. I think I'm missing a power of 2 here. So 1 over d factorial raised to the power of d times determinant of the best subdeterminant of size d here, corresponding to T star. OK, and this is just the guarantee of the greedy algorithm. OK, so I have some bounds for the initialization. And I also need to bound just the determinant of the maximum determinant of any of subset of size R, M star. And this is also very similar. So again, I use the Cauchy-Wiener formula. This is the bound. Right. And now, since I know that the number of terms here is R choose D, and each subdeterminant is less than just the max determinant with the D vectors, denoted by T star. So then I get the bounds. So I get these bounds for the optimum, and I get this bound for the determinant of the initial matrix M. And since in each step I increase by a factor of 1 plus delta, this is just a number of iterations, b times log R over delta. OK. And actually, the computation for each iteration, if we just do it naively and do not do anything like sketching or something, we get just n times R times d squared. So that would be then the total runtime would be something like, and R is also order d. It's more or less like n d to the power 4. But if you do some sketching, you can actually get better dependence. You can get rid of n, for instance, and get some NNZ of the A and so on. Okay. So any question for the runtime analysis? I think it should be clear. Good. So now let's see maybe actually the more important question. So why after the algorithm terminates, I get the result that I wanted. So I have the coefficient vectors with the small norms, L2 norms, let's say. Okay, so this is actually what I will have when the algorithm terminates, right? Then I know that for every j that is not in the spanner, I cannot swap it with anyone in the spanner and improve the determinant by 1 plus delta. But my goal is to show that if I look at the matrix whose columns are vectors in S, then for any points Vj or any vector Vj, there exists a coefficient vector alpha j such that U alpha j is equal to Vj, and the L2 norm of alpha j is less than 1. And this is my goal. Okay, so first of all, let's see if we can get a bounds for alpha j here. So in general, if I write the alpha, if I want to solve for alpha j here, I can just take this minimum norm solution, u pseudo inverse time Vj, and if I compute now the norm of alpha j here is basically Vj transpose UU transpose inverse Vj, which I just write it. It would be Vj transpose m to the power m inverse Vj, which I define it as tau j. It's also leverage scores in some sense. So basically, that's interesting, right? The object that I need to work with is basically related to what I'm keeping track in the algorithm. And we'll see how we can now relate these two values. Okay, so I'll talk. So we should then define the tau I as just Vi transpose M inverse Vi, and Tij as Vi transpose M inverse Vj. So these are the leverage scores for the I in the spanner set, for instance. And actually, they have some nice properties. For instance, the sum of these tau I is equal to D, and they're also symmetric. Tau ij is equal to tau ji. Okay, so now let's check again the condition that we have. So we stop at this point. If the determinant of this object is not more than 1 plus delta times determinant of m, then we just stop the local search. And we can actually simplify the left-hand side and write it as determinant of m times 1 minus tau I times 1 plus tau j plus tau ij squared. And it's actually not that hard. We are using some matrix determinant lemma and Sherman-Morrison formula. You can get that bound. Okay, but now everything looks very good. They are in terms of tau I, tau j, and these are the things that I want to show that are bounded, so that I can show that the L2 norm of the coefficient vector is bounded. Okay, so that was what I wanted to show. And to see that, this is what we have for every j not in the spanner and every I in the spanner. I know that this holds. And then for fixed j, just sum over all I in the spanner. I'll get these things for the left-hand side, and right-hand side just becomes simply R times 1 plus delta. And if you just do the calculation, we get basically tau j is less than d plus R delta over R minus d plus 1. And setting the value, for instance, R to 3D and delta to 1 over 3, we get the L2 norm less than 1 for everyone not in the spanner. Okay. So actually, I just described the local search when I don't allow for repetition, but I could do that as well. You can also run it with repetition, and then we will have this result for everyone. But here, for the case of volumetric spanner, we actually don't need to do it with repetition, and just we don't allow repetition for volumetric spanner. But later for MVEE, I mean, it's important that we allow a repetition.
Quick question. So, I mean, so existentially now you could get a stronger result, right? Don't you get like 2D? So if I put delta equals 0, so if my algorithm runs until it cannot,
Okay. Yeah.
right? You get
Yeah,
you get a 2D
Yeah,
size.
that's, I mean, yeah, existentially, yeah.
And then that matches your bounding box.
Yeah. We care a lot about the runtime. We shouldn't. Okay. So let's see what it gets for volumetric spanner. So I just described the algorithm for p equal 2, right? So I mean, you just run the local search, and it finds L2 spanner of size at both 3D in polynomial runtime. But that's a good point. I mean, we show also that there exists a 2D one. And for p equal to 1, I said that it's actually it's completely different from the case for p equal 2. To see that, I mean, there's a very canonical, somewhat construction. Just consider the almost orthogonal vectors in the d-dimensional space. So V1 to Vm's are almost orthogonal, meaning that their inner product is just order of log m over d, is square root of log m over d. And we know that there exists just exponentially in D, many of them. Okay, and then it's easy to see that any L1 spanner of size less than m, even you just ignore one of them, need to have L1 norm for coefficient vector at least omega of square root d over log m. The reason is that because just everything, I mean, if you write it in the canonical form of this inner product, I mean, all of them has just a small value, so the L1 norm should be large. Actually, we can show that this, what you get from the L2 spanner and just doing the Cauchy-Schwarz, you get actually the matching bound here. You get this bounds on the L1 norm with just order D vectors. So basically, this is optimal. And again, using the Holder inequality and the lower bound that we have for p equal to 1 and the bound that we have for p equal to 2, we can also get these bounds for any p between 1 and 2. Okay, so we cannot hope to get the norm better than d over log n to this power, and we have the upper bound that get d to the p over 2p minus 2. And it's about the norm. The size is still 3D. Here, at least, I mean, we have the size 3D or 2D existentially. Okay. And for p greater than 2, is just simply follow from the L2 spanner. Right? You can just use the L2 spanner, and this is still size is has size less than 3D. Okay. So I want to summarize here and maybe just mention a few open questions. So basically, what we did was just the analysis of a simple local search algorithm for volumetric spanner. And I mean, it's important. I mean, we have tons of application from the bandit linear, multi-armed bandit, or online linear optimization, matrix sketching, and so on. So, and hopefully you can find more. And that was the open question that was raised by Hazan and Carning. They showed that there was a 12 times the upper bound, and they showed a lower bound of d plus 1. So we make it down to 3D and actually 2D, as you mentioned, existentially. So, but yeah, it's still an interesting question to see what can be done here. And there was actually some gaps for other norms that I showed. It was, but basically not on the size, on the guarantee of the norm of the coefficient vector. So it's an interesting question to see what's actually the right value there. And I hope, I mean, that you can find some nice application of this object in design algorithm in different areas. And that was mainly the purpose of my talk. Thank you. If you have any questions.
Any more questions for Holly?
If I have time, I can go through some MVE, but yeah, I don't know how much time do we have.
Sure. I have a question.
Sure.
Just ignore this two like, if I just had a set of vectors where every vector is 1 on the first entry, and then on the rest of the entries, it's like either it's like a 1 on the first entry and then a 1 somewhere else, or a -1 somewhere else. It feels like a case where like 2D would be optimal. Like if you thought of, are these cases like this deep? I don't know. D+1 sounds like a really weak. Is there a chance 2D is just the best you can do? I mean, we could take it offline. I just wonder if you've thought about these lower bounds at all. Or...
Not actually, we haven't thought about it. So,
Okay.
but I mean, the lower bound that, for instance, the things that we know for maybe bounding blocks also somewhat suggesting that 2D might be the right answer.
Yeah.
That makes sense. Yeah.
Okay, cool.
So at the beginning, you said that for the L infinity norm, we do know that D is possible, right?
Yeah.
Do we have any understanding what happens between 2 and infinity then?
So I mean, everything that I mentioned for 2 will apply for that, right? So, for instance, 2D existentially exists. We know we have it. I mean, by the guarantee of L2, you have guarantee for anything larger, right?
Oh, gotcha. Right. Okay.
So
cool.
that's clear. But yeah, in terms of the lower bound, if, for instance, what's the right answer, we don't know. Yeah.
Fair enough.
I mean,
Cool.
again, the same question. Yeah.
Sounds good. Thank you.
Any final questions? No, let's thank Ali once more. So we now have lunch, and please be back by 2 p.m.